So, all right. Good morning, everybody, or whatever daylight it is, or daytime in your time zone. Welcome to the last day of talks of ACCU 2021. My name is Andreas Fertig. I work as independent trainer and consultant for C++, and I like also to speak at conferences to share my knowledge. I'm also the creator of C++ Insights, a tool you may or may not have heard about. I will use it once or twice in this talk today. The talk's topic today is C++ 20 templates, the next level, concepts and more. And there's really a lot to talk about. Could fill probably an entire ACCU track. So let's start right in. But before we start, let me tell you a short story about me and my last name. My last name is Fertig, and this is an adjective in German. You can translate it to finished, to ready, complete, or completed in English. It's quite nice because some project managers think once I'm on the team that the project is finished. That's of course not true. It can be true if I finish the moment the project is finished anyway, but there is no string attached with my name to that. There are also sometimes issues with my last name because as an adjective it's spelled with a lower first letter, while as my last name it's spelled with a capital first letter. So somebody tells me you are not hearing my sound, but others tell me you hear it. Okay. So I continue. I constantly fight with my spell checker because as an adjective, my name, my last name is spelled with a lower first letter, and as my name, it's spelled with a capital first letter. So we still haven't settled who is right when, and it leads to some issues at a time. There is another thing, probably two other things that come with that name. One is that it took me over 30 years to learn that I mispronounced my own last name. Because usually if I introduce myself, at least in a German context, I say Fertig, with more or less a K or a hard G in the end. But proper German, it's Fertig, with some ish sound at the end. And well, apart from Germany, where I come from or where I grew up, they like to spell out things with hard letters. So that's why I mispronounce my own last name, well, partially sad. You can confuse people with my last name. Back many years back, during my apprenticeship, I had sometimes to answer the phone. And one of the first times I did this, I picked up the phone and I said, Fertig. And the person on the other side was heavily confused because to them, I told them, finished, ready. So it was a little bit offensive to at least one person. There was a small complaint later about me answering the phone and the way I did. And it took some time to resolve the situation and tell them that my last name is indeed Fertig. So yeah, but it was still fun. Enough about German and last names. We probably come back to this missing link. It would be better back then when I answered the phone if I had said Andreas Fertig or Mr. Fertig at the phone, but we will see similarities in C++. So let's start with the actual topic of the talk, C++ concepts. There are a really, really amazing feature in C++. With concepts, we can formulate requirements for a type. That's slightly comparable to what we can do or could have done in C++ 17 with std enable if, but it's so much more powerful than a plain std enable if. Concepts consist of the definition of a concept, so a name we can refer to. This is introduced by a new keyword, concept, and they consist of requirements, which we have another new keyword for, which is requires. And we'll see pop these new keywords up in a lot of places. The figure you're seeing here in the middle of the slide, that should give you an overview about how a concept definition looks. It starts with the template head, because concepts are meant to be for generic things, so they are templates always. Hence, they start with a template head. And we can use there everything we can use for templates we knew before concepts, so function templates, class templates, or whatever. We can use type parameters, we can use non-type template parameters. And after the template head, we see the new keyword the first time, concept. This introduces that this thing is not a variable template or any other kind of template, it's a concept. And then we give that thing a name. I choose a poor name here, probably my concept. And then after the equal sign, we assign requirements to that concept that must be fulfilled. We can use there with stud_same a concept. Stud_same comes with C++20 in the standard library. And we can use Boolean operations like AND or to piece multiple requirements together. And here I'm using now type traits to say either T and U must be of the same type, and is class V or is enum V must be true as well. So here we have an OR condition. These are the requirements. So this is a concept. This is what we talk about basically often when we refer to concepts. Let's use this and peek a little bit behind how we apply this and then how we can build something up. The task should be the following. I like to have a function called add, which should be able to add multiple parameters together, multiple values or objects, depending on how you like to see it. So x and epsilon, I'm adding 2, 3, 4, 5, and an epsilon 2, 3 together. So obviously we are looking at some kind of a variadic thing, most likely a variadic template. And then we have the last case set, where I have 2, 3, 3.14. And this last line I don't like. I don't want this to compile because I'm mixing types here. I'm getting some promotions. Most likely my integer gets promoted up to a double, to a floating point, and I don't like this. So the most obvious way is we shoot on this with a static assert and preventing this code from compiling. But for the purpose of this talk, let's assume that we like to leave the room open for another application area, for another developer, coming up with a very smart idea or very specific use case where this add should work. So I don't like to apply a static assert here to close all the doors. Okay, so let's see how we can approach x and epsilon. This is my try. It's C++, so you probably know a different solution. The grayed out part here, that's boilerplate code. I need to make the rest appear a little bit nicer. What I'm doing there in line number 2 is I'm creating a new type trait or a variable template called rSameV, which uses stud conjunction v from C++17 together with stud is same, and it basically compares whether the first type is equal to all the types passed in the parameter pack TS here. That's what rSameV does. And then I have another helper, which basically is in line number 10 in the upper code example. It's first argt. And what this thing does, together with the struct, I provide a parameter pack to it, and it gets me the first element of this parameter pack, and I can access it via the : type member in my struct first arg. Okay, that's code I also in parts need for the concept solution, which we'll see in the next slide. But this here is the C++17 approach. And below we are looking at the, I would say, real part of the implementation. There I have my variadic template, in line number 1 with the type name ... And then in line number 3, we have the function name add and the parameter pack in form of args. I mark this function no except. And then in line number 5, I use C++17's fold expressions to sum up all the arguments in the pack that are passed to this function. It's implementable in C++17 or 14 as well, then without fold expressions. So this is a compact version. And it's okay, except for line number 2, if it comes to me. I really don't like line number 2. What do we have here? We have a std enable if t, which uses my previously introduced custom type trait rsame v and first arg t. Of course, I assume a lot of you, if not all, know that std enable if t takes as first argument the Boolean condition. This is my rsame v, which tries to figure out whether all types in this provided pack are the same or not. If yes, it yields true. If this yields true, my enable if sees that the condition is true and uses first arg t. So it gets out the first argument of the pack because all arguments in the pack are of the same type. It's okay to just get out the first one. And then my enable if t returns that in some sense. So it's inserted here because this is our return type. Because there is no other place where I specified the return type of add. So this whole line number 2 tampers with the return type. This is my preferred way because that way I'm staying mostly out of the way of users. Introducing defaulted either template arguments or function parameters always has the temptation for users to provide a value there because it appears in their syntax highlighting, their IDEs shows to them. So this is the way where I prefer to apply it because it's obvious that no one should provide a value here. But it's so hard to read. And it takes a lot of time to explain it, especially to people who are either entirely new to C++ or at least new to templates. And of course, I could also choose to use a trailing return type here. Then at least I have the auto in front, but then I have to put this whole enable if in the trailing return type. So it's slightly better, but not a real win in my eyes. So this is the kind of code that scares people away from templates. At least this is my observation. This is the same code using C++20's concepts. I left out the helper code because that's the same. That's the reason why it was grayed out in the previous slide, because it's used in both versions. So let's look at this. What do we have? Line number 1 is the same. We have the template head. It's still a variadic template. Line numbers 4 to 7 are the same. I have my function add here, which takes the parameter pack. It is no except. And in line number 6, I'm using C++17's fold expressions to sum all the arguments up. One difference appears in line number 4, and this is that I immediately have my return type here, which is auto. I don't need a trailing return type. So this is my function definition. And the beauty of this solution is line number 3. Requires rsame v. This is highly readable. This is more or less a specification. This expresses that this function add here requires rsame v. We might not know what rsame v is. Might have to look it up in the previous implementation, but it is clear that this is a requirement. In the previous slide, nice dot enable if, well, we learned to interpret it as a requirement, and we know that this thing will not work if RCMV is false. But this is code I can teach to a lot of more people in way less time, because it's so much more precise, down to the point. It expresses what I like to express here, what this function is about. And this is also concepts. When we talk about concepts, it's often about the keyword concept and the concept which we can refer to with name, but requires us the runway for concepts. We need this to build concepts in a lot of places, and we can use it even without concepts to make our code better. So it requires as part of concepts. It's hard to distinguish this feature and it's all elements. But this is the basic of all this. It's C++, so we have a lot of application areas for concepts. This figure here illustrates it. In the template head, I can introduce now a type constraint, here C1, which is a concept. So instead of writing type name or class, I can now simply put my requirements here, my constraints, my concept. I can now say, what should this type be? What properties does it need to have to work with this function fun here? I know a lot of people who ask me, should I use template here, type name here, or class? When should I use one? When should I use the other? Now we can be more precise. We can come up with the concept, with the real constraint this type has to fulfill. Next, after the template head, this is what we've seen on the in our example with add. Here I have the so-called requires clause. This can use a concept as well, C2. In the add example, I use the type dirt here. So at this point, with the requires clause, we need something that yields a Boolean true or false value at compile time. And then there's another thing called constraint placeholder type. This is C3 and C4, has nothing to do with an explosive at this point. It's C++. You can shoot yourself in the foot, but usually you hurt only yourself. So constraint placeholder types, they allow us to restrict or constrain auto types, auto variables, auto return types, and auto parameters, which we got with C++20 as well. So C3 here, and it's not C3PO, it's only C3. That says that the return type is still auto, but it comes with a couple of constraints named in C3. C4 here is really a new part because we now can have auto parameter types in regular functions. We will see more about this later. We know this from C++14's generic lambdas. Now we can use the same syntax for regular functions as well. And here it's the same as with the auto return type. We can constrain this auto type. And then in C5, we are looking at the trailing requires clause. This is much like the trailing return type. Here we have another way where we can specify a concept or a requirement for this function in form of C5. Okay, so these are the various application areas for concepts. We'll see a few of them during this talk, but not all. Coming back to the previous add example. If you look at this, we can say that there's a little bit more we can do, because currently add only prevents mixed types, which is what I asked for. But the current version also leaves a lot of things unspecified. So add can, without any sense, being called with only a single parameter. The name of this function is add. That implies that at least one thing is added to another. There are likely some corner cases in generic code where you're coming from a parameter pack and may end up with only one element in this packet calling add? Maybe. But the question still is this what you like? So for now, I would say it makes no sense to have a function that's called add that doesn't add anything. So we require at least 2 parameters for add. In C then, the type used in args must support the plus operation. That kind of may be obvious from the name add. But what does it mean? Is it the operator plus? Does the object has to have a method called add? We saw it on the slide. I used the operator plus, but we have to look up the implementation to know what's going on here. And if we are passing in a type that doesn't support the plus operation, we are getting one of these page-long error messages from the compiler. So flipping over to the Q&A part here, I try to answer that on the go. What is the difference between the trailing requirements versus after the template head in terms of usage? So let me jump back one slide, if Zoom allows me to. We will see this later in the talk. You can use the requires clause only if you have a template head. So if you have a template. And there are some cases where you don't have or don't want this function fun to be a template. And this is one reason or one application area where we can use the trailing requires clause. We will see that later. So getting back to my there is more. We have 2 more requirements already processed. And then in D, the operation plus should most likely be no except, since my add function itself is no except. But this isn't checked so far. And I personally would not like to wrap a simple addition of integers in a try-catch block. And then we have another thing, the return type of this plus operation. That should match the one of args, so of the first type in our parameter pack. Once again, that there are sometimes reasons why it is this plus operation might return a different type. Maybe because it returns a proxy type or something like this. But for now, let's say that this is the set of requirements we have for this add function. And maybe pause a moment and think about how you would implement that in C++ 17. And while you're doing this, let's have another brief chat about the basics or a bit of theory. So this is a requires expression. Remember before I talked about a requires clause. This here now is a requires expression. 2 different things. A requires expression can be seen a little bit like a function. It starts with the requires keyword. You see, we have another application area for requires here. And then we have a parameter list to this requires expression. We can define this one freely. The T and U here refer to it being used in a template context where I have the template types T and U. I can make them also T star, T ref, mix in const. You can start another West Coast or East Coast discussion here. It's absolutely like every other parameter list of a function. We can use built-in types or types that are present in the type system, like int, jar, or my class, whatever. So this is very much an ordinary parameter list. It's only used at compile time, and it's only viewed as types. So nothing is really executed here. And it's really powerful. We will see that later. And the body of this requires expression has a single requirement, and that is that it has to consist of one or multiple requirements. Isn't that beautiful? My requires expression comes with the requirement itself. Beautiful. So that means I can list requirements in this requires expression. Now we've seen requires clause. We are looking at a requires expression. That's not all that easy probably to digest. You can see this requires clause, which we saw 2 slides ago, in the requirements C3 and C5 as a Boolean expression. And the requires expression is a thing that's a slightly different, more complicated, but we already know this from no except. Hello, no except. Remember, we can either say that a function is no except or isn't, and we can query with the same keyword whether a function is no except or it isn't. And this is comparable with no except here. We can see a requires clause, like we saw it 2 slides ago, like an if that evaluates a Boolean expression, and this requires expression yields us such a Boolean value. Okay, that this is what a requires expression is about. We can there combine multiple requirements, and this in a much better way than just with Boolean and or, because a requires expression supports 4 different kinds of requirements: a simple requirement, a nested requirement, a compound requirement, and a type requirement. For the purpose of this add example, we will only look at the first 3 because I couldn't come up with a real good example why I would need a type requirement there. So simple things first, we start with a simple requirement. A simple requirement checks whether an expression is valid and will compile or would compile. So in line number 1, I introduce my requires expression, and in line number 3, I have this simple requirement. It is a little bit due to this, let's say, slide code here and my example add, that I have to repeat this fold expression here and later once more, which is something I regret, but in larger real codes, you will see such a repetition only rarely. So what does this thing do here in line number 3? I have this fold expression, and what a compiler does is it tries to instantiate this. So by that, it will figure out whether the types in args support operator plus. And if not, it will yield false, and my requires expression yields false. And if yes, this whole expression and my requires expression yields true. With that simple thing, we already successfully checked our requirement C. Arg must provide a plus operation. And below here, in the gray code, I show you what's no longer working now. If I simply define a struct called noadd without operator plus, add will now no longer compile with this requires expression attached. This is a simple requirement. And then we have a nested requirement. And this nested requirement is probably also very nesty because it can confuse you. The nested requirement you see in line number 4 and 5. And now you see that in a requires expression, we use once again requires. It seems to be a very popular keyword in C++20's concepts. The purpose of a nested requirement is that it evaluates the result of an expression to true or false. So what we are looking at in line number 4 is that with the requires in front, the compiler checks whether our same we yields true. It not only tries to instantiate it, that's one part of it, but then it also looks at the result. Without this requires in front, we are back or down to a simple requirement. The compiler would only check, is it possible to instantiate that? Yes or no? So forgetting this requires here gives you a different kind of requirement, and with that a different result. So remember, always put the requires in front to get a nested requirement. In line number 5, we see the same pattern again. Here I'm now checking whether my parameter pack contains more than one element. Without the requires in front, this whole expression will, well, 99% of the time compile, because as long as I have a parameter pack, I can apply the size of operation, and the compiler will just say, well, it's boring morning, but if you really like, I instantiate that thing for you and throw the result away practically. Because it's possible, it's always possible. Below we see now that 2 other things are restricted now. My requirement A, B, and C are all now no longer working with this requires expression. I can no longer below in B call add with only a single parameter, and I cannot call it with 2, no add. So perfect. Now let's look at another requirement. This is the compound requirement. A compound requirement checks the return type of an expression, and you can recognize it by the curly braces. We see this in line number 8, 9, and 10. I commented line 8 and 10, 8 and 9, because 10 is the combination of both, but I like to show all the versions to you. So in line number 8, I'm starting this compound requirement with the curly braces, and there I have to repeat my fold expression once more, which is the thing I'm sad about. And then after this compound statement, I put no except. And this makes the compiler check whether this entire expression in line number 8 is no except. And by that, I get a check whether my plus operation is marked as no except. Only if the answer is yes, this requirement would yield true. In line number 9 now, I can do another awesome thing. It's once again a compound requirement. I have the curly braces, I have my fold expression in there, and then you see this arrow, like the trailing return type, following this compound statement. And then comes a concept. This is a place where you always need a concept. In this case, same as. And in this concept, now I'm using first arg T. And this is the helper I created in the beginning. And those of you who are quick enough reading this code will realize that I'm saying here same as, but I only provide one type. First arg T yields a single type. So the same as what? And the answer is the compiler gives us access to the type returned by the expression in this compound statement. So it gives us access to the type yielded by this fold expression. There is no name, we cannot grab it, but the compiler knows it, and the compiler can grab it, and it inserts it into my same as in the concept as a first parameter. And by that, implicitly, I have 2 parameters here. Now we can combine these 2 things in a single statement. This is line number 10. This is the one I'm using actively in the code. I do use the same syntax. I have the curly braces, I have the fold expression, and now I can say no except as before. And after no except, I can use this trailing return type syntax and then my same as concept to check at the same time whether the entire operation is no except, and that the return type equals the first type in my parameter pack. And with that, I do fulfill the rest of my requirements for my add function. Now, a couple of other things don't work anymore. I have, aside from this no add struct, I have another struct created, not no except, which has an operator plus, but doesn't have it marked as no except. And then I have another type, create a different return type, which has an operator plus, which is no except, but it does have a different return type. So all requirements A, B, C, D, and E now no longer compile. Let's piece that together. We created this requires expression, and here is it combined into our add function. The requires expression we created is the gray part of this code. We had before in line number 1 the template head making it a variable template, a variable template, and then in line number 2 I start my requires clause, which then is followed by the gray part, the requires expression, and below in line number 9 to 12 we have the actual contents of our variable function with the function name add and default expression. Whenever you spot something like in line number 2, where you have the tokens requires directly after each other, this is called an ad hoc constraint. And we can do this, but it is also a first sign of a code smell. Because we spend so much time creating this requirement and now we can no longer refer to it. We cannot reuse it. We only can use it in this single place, except if we copy it over to another. But this is duplication and probably not what we want. The probably better choice is to define a concept. In line number 1, I start the template head for my concept. It's a very part. And then in line number 2, I introduce or start my concept with the keyword concept. I give it a name. I chose edible here. And then after the equal sign, we see in the gray part, once again, our requires expression. And now below in line number 10 and 15, I do have my add function. And in line number 11, we now can see the requires clause using my concept edible. Not only is this a little bit more readable, because if you're only looking at the function, it's very clear now that it has to be edible. We can always discuss the naming here. But edible is also reusable. And if you remember on the last slide, I said it's probably a code smell, and here I'm saying it's probably better. And the reason for that is that this is a very specific thing I created here for add. And it's a question whether you really need or can reuse that or not. So this is why we have ad hoc concepts. Sometimes it makes sense to have it only in this single place, but on the broader scope, we should have a real concept, so something with a name on it that we can reuse. So I'm seeing another question here. How would we check whether a dependent type exists by naming it as one requirement? A dependent type. I think I don't have this in the presentation. We can discuss this after the talk. And I see something else here. Is line number 4 actually needed once? We have line number 7. This is back to this. We have line number 7, presumably for the return type of the operation to be valid. The operation has to be possible. So it's probably this one or another one. No, it's 3 versus 10 in this slide. Yes, this is a question I get often at this point. This is one reason for the duplication. And basically, we are looking for different things here. One is a simple requirement, is this possible? And the other thing gives us more or less the answer is the operation no except, and is the type the same? Of course, without line number 3 being there, line number 10 would also cover this check. The difference is a little bit in the error message the compiler will give you probably. So you have to figure out on your own a little bit if it's better to specify all the requirements to also make them stick out. Here in line number 3, I can see that's a simple requirement, so this has to work. And line number 10 basically is about something else. We can combine this, and yes, without line number 3, the same would be achieved. I hope this helps. Yes, and you're assuming the error message would be different. As far as I've seen it, that's true. Yes, the error message is different because you're doing different things here. But in sense of reducing maybe the code duplication here, especially from this fault expression, it can be the right way to go to say you don't write line number 3 and only line number 10. So I mark this one as answered. And I do have another question. Do you think that concepts cover all the use cases of std enable if and std void t, or what is left out? We will see that later. That's an excellent question. And it's C++. So no, I don't know what all use cases can be. I'm learning new things every day. So I'm not sure if all will really cover it. So we define this concept. Now we spend a tremendous amount of creating a concept and assume it's production code, then you spend probably more time, more discussions around it. And now we have all this working. Assume you tested it with at least one combination of integers or so, and it yielded true. All right. But maybe we should test our concept, because concepts tend to be something bigger than just a trivial true or false check. As I said, we spend a lot of time creating such a simple concept. So what I'm doing here is I'm creating a struct called stub, which is also a template. It takes 3 non-type template parameters, no except operator plus and valid return type. And internally then it provides either an operator plus or it doesn't. This one is either no except or it isn't. It yields the correct type or it doesn't. So this is just my stub to create all the different types I need for my check. And then in line number 16 to 19, I'm using aliases to make it readable. I have no add, valid class, not no except, different return type. And I'm parameterizing my stub with the different parameters to make it match my description here in the using alias. And because concepts are things that are available at compile time, I can now use a simple static assert together with my newly created type to test my concept addable. This is another reason why it may be good to create a concept instead of an ad hoc requirement, because now I can directly test my concept. The same is also possible if it is an ad hoc requirement, then I have to test the function. But I decided to not go into this and show the simpler thing today. So in line number 2, my static assert checks that addable returns false if I pass in an int and a double. In line number 5, I'm checking my requirement B. Addable returns false if it's called with only one type. Line number 8 to 10, I check my requirement C. Does the type has a plus operation? 2 ints to have it. My valid class has it, but my no-add class doesn't have it. So my static assert checks that. Line number 13 checks my requirement D, that my operator plus is in fact no except. And then in line number 16, I'm checking my requirement E. Addable doesn't work with 2 different return types. You can add more checks. You shouldn't probably add less. So think about this when creating a concept, whether it's an ad hoc concept attached to a function or a concept with a name. Check it. There are more powerful things than we had before in our toolbox. Now, C++20 gives us something else that's attached to concept. And this is abbreviated function templates. Here's my motivational example. This is code I wrote often in the past. I like it. I have a function called doLogged, which acquires some kind of mutex internally in line number 4 here, and then it executes in line number 6 the function f. And this function f is a parameter that is passed to this function. So doLogged itself is a function template. This code is, for me, really useful. I need it in a lot of places, but it comes with 2 downsides. First, people complain about the template head. I do have to write a tremendous amount of characters to make this thing come alive. And then the more concerning part to me is f, my parameter, has to be a callable. This is not obvious. Of course, you can start writing a lot of documentation about this function. Maybe a brief line does the job. But hey, the compiler doesn't care for comments. It only heats up your CPU. And other people may also not see the comment because it's in the wrong place, or they simply didn't look. So this is not obvious that we have to pass a callable in here. This is C++ 20. The template head is gone. This is an abbreviated function template. And an abbreviated function template is it if there is a single auto parameter in it. Then we can skip the template head. We can also apply it, but let's not get too complicated today. This is an abbreviated function template. It spares us writing the template head. And by that, I now have the chance to say that what this thing takes as a parameter must be invocable. There is a concept stood invocable in the C++ 20 standard library, which helps us out here. So now I have not only written less characters because I don't need a template head, but I also have the documentation in place where people do care about, because we see it popping up in our IDEs and the compiler checks it. And this is the most valuable part. So I promised you, I think, a little bit of C++ insights. So let's do that now. This is C++ insights. You can punch in your C++ code on the left. You get C++ code out on the right. Awesome, correct. It's not that hard. The difference being that what you're getting out on the right is code that is enriched by all the things the compiler does for us to our code. And in this case, we are seeing a template instantiation here. For this part, I'm not going to talk about a lambda, which is below here. So this is the instantiation of my doLogged function, which, if you look over here from our input, is no obvious template. But it is due to the auto parameter. This is how it's modeled internally. It becomes a function template, and hence we are seeing an instantiation for this function template here. So be aware of that. When you're using abbreviated function templates, it comes with the name. It's an abbreviated function template, so it's still a template, and this always comes with the auto parameter. So I'm checking the questions here. Can a concept be used instead of type name within a template header for variety arguments? Would it then be executed for every type argument individually? Yes, as far as I remember, you can do that. You can use it even for a variety parameter pack. I couldn't use it here because I had the constraint are same, and you described it correctly. It will be called, the concept will be checked for each parameter in this pack individually, and I do not have access to the entire pack. So that's why I didn't show that here. So let's move on. This is probably the most powerful example I could come up with when it comes to templates. aware that this is not code most of you write on regular basis, except if I'm having a crowd consisting of only standard library implementers here. What I like to do is I like to write a wrapper which behaves the same as the type it wraps. Okay. I have therefore my com-like struct, which emulates what Microsoft does with their com things. The destructor does nothing, but it's present. And I have a function called release, which releases the actual data. And then I have a different struct, which is called default destructible here in C, which is just an empty struct type. My two static asserts in line number 11 and 12 then check that a thing that's called wrapping a com-like struct is in fact not trivially destructible, while if my wrapper wraps a default destructible type, then it should be default destructible. So we like the same behavior for our wrapper as the type it wraps. One attempt to do this is C++ 17 here. I have created a type trait called hasRelease, which in line number 5 uses decal type to evaluate with the help of stud decal val whether there is a release function present for this type. And then in line number 14, I'm using a const expr_if together with this hasRelease to check whether this thing, my type T, has a release method. And if yes, I'm calling this. Practically, this works. Release will also only be called if there is a release function or method in this class, but I always have my destructor. So this type will never be default destructible. Okay, despite the fact that this const expr_if will evaluate to nothing if there is no release method present, I still define the destructor. And getting around this involves a lot of code. It involves deriving from either a default destructible or not default destructible helper type to make this right. So library developers have their fun with that, or standing in a corner and crying about this. This is C++ 20. And we before had the question where it makes sense to apply this trailing requires clause. And this is one place. Look at line number 6. I'm in the class template, but my destructor still isn't a template. Even in C++ 20, we cannot define a templated destructor. That's not a thing. But in line number 6, I'm now starting a requires clause, a trailing requires clause, which then contains a requires expression. So we are looking at an ad hoc requirement here. And this requires expression says that it takes one parameter of type T called T, and in its body, it uses a simple requirement to check T.release. That's it. And then in line number 8, of course, it calls release if it needs to destruct something. So line number 6 gives me a conditional destructor. This destructor is either present or it isn't, and it depends on the type's method's existence of release. So has this type method release, then this destructor exists. If not, it doesn't. This is something you couldn't achieve that easily before in any C++ standard. Okay, you needed to write an awful lot of code to come up with precisely this. Because the beauty is in line number 11, I still have a defaulted destructor. And now you can wonder, are there two destructors going on? How does the compiler decide? And there's another thing going on, which is called concept subsumption rules. The more constrained a function is with a concept, that one wins if it's true. So in our case, if we have a type with a release method, the most constrained destructor is that one in line number 6. So that one will exist in this wrapper for this type T, and the one in line number 11 will go away. And the other way around, if the type has no release method, then this whole part in line number 6 to line number 9 simply goes away, and we only have our defaulted destructor. So this is the power of concepts. And you can not only apply this to a destructor, but to any other method. Let's depart a little bit from concepts. There is something else, and that's conditional explicit, which is new in C++ 20. Here I have in line number 1 my struct B and another struct A in line number 3. And this struct A comes with a conversion constructor marked as explicit. This is the bubble A here in line number 5. And then I have a function fun in line number 9, which takes an A object. With the code as present, I can call fun in line number 13 with an A object, but I cannot call it in line number 14 with a B object. This is exactly what I like. Now, because we talked about a wrapper before, let's say we like to employ another wrapper here for our type. Now my function fun takes, instead of just A wrapper of A. And below here in line number 1 to line number 5, I present this wrapper to you. It's of course a struct template. It has a conversion constructor, which is also a template. The issue here, once again, is line number 13 now compiles. Because of this conversion constructor in line number 3 and 4 being a template, it's not marked as explicit. And figuring out whether to mark this explicit or not requires duplicating these 2 lines of code, attaching an enable if to it, and spinning out depending on whether you figure out that U is convertible to T or it isn't. So we have to write more code to make this thing behave correct in the sense that our wrapper should emulate the behavior of the underlying type. Now C++ 20 gives us the option to have a conditional explicit. So we already talked briefly about the no except operator. Here it's the same. I now can say in parentheses true or false to my explicit. And of course I can use type traits here. So what I'm doing here is I still have the same conversion constructor, just that this time I'm saying explicit and in the parens mark it as not explicit if U is not convertible to T. Or if U is convertible to T, then mark it as not explicit. This is the power. This once again saves us lines of code. In this case, it saves you 50% of the code you have to write. That's always a good pitch for management. But it does even more, because now you have a single function which is always instantiated. And only the explicit depends on a type trait. There is a chance that your code becomes faster in sense of compile time. Because in the previous solution I didn't show you, I only described with the enable if, you basically have 2 methods, only one of them survives, but the compiler has independently to figure out which one. Here, much better for the compiler to know what we like to express. And this now works. It emulates the behavior of our underlying type. There's more. I also had marked my conversion operator in line number 4 here as explicit. And if you are looking down here at line number 18, this once again should not compile, because at the top, line number 4, my conversion operator from A to B is marked as explicit. And my wrapper as presented here, as we had it before, doesn't do this. Only my constructor so far is marked with the new explicit. And I saw it in too many places that people only talk about a constructor, but it's explicit. You can apply it to an operator as well. So I can also mark my conversion operator here with explicit. It's the same syntax, it's the same notation as above. The only difference is this time I'm checking whether T is convertible to U, while I'm checking in line number 10 whether U is convertible to T, so it's the other way around. And now I'm needing a static cast in line number 19 to make my assignment of an A object to an B object compile. This is, once again, saving us lines of code. It makes our code more expressive and clear. There's another string attached to this. What I presented so far was more or less the motivation for this feature, and you probably use it in highly generic code and in other things. But think about this. Imagine you're in a code review situation and you are first approaching struct A on the left. Struct A on the left has a conversion constructor from int to A, which is marked as explicit. Wonderful. You can have a check mark in your code review checklist, conversion constructor marked as explicit. Wonderful. No further questions. And then later on, you are approaching the struct on the right, B. It also has a conversion operator, conversion constructor from int to B, but it isn't marked as explicit. This raises questions. Did the author of this struct B forget to mark it explicit? Did they leave it out on purpose? We have to ask. Maybe there's a comment, once again, telling us this is intentional. I personally think comments are more the dot on the I than anything else, because they tend to get false over time. So you may have left a comment here right now that it is intentionally not explicit. And in the future, maybe this is no longer true, but a comment is still there. So I like my code to do the actual work, and the comments only the explanation stuff. My conditionally explicit can help me here out, because now I can leave a clue. I can now say here in line number 3 on the right that yes, I thought about this. And yes, I intentionally mark this conversion constructor of B as not explicit. This gives us a new way of expressing things here, because the other way was absence. And absence is always raising the question, is it intentional or not? This is, remember the story from the beginning with my last name, when I answered the phone and only said my name. It's the same here. Now it becomes clear. This is me just saying my name and confusing people because they think they have to be finished already. And now I tell them I'm Mr. Fertig. Now they know what they're dealing with. This is the other angle of explicit. Let's come back once more to concepts. One thing we haven't talked about is error messages. What this code here does is it checks whether a given type is a standard library container. And for that check, it assumes here in line number 7 to 16 that a standard library container comes with a value type, with a size type, with an allocator type, an iterator type, and a const iterator type. 5 types. And it must have a size method, a begin method, an end method, cBegin, and of course cEnd. So 5 methods. This is basically what defines a standard library container. Once again, it depends on where you're coming from, what's the code you are usually working with. Either this is daily code for you, maybe it's intermediate code, maybe it's totally scares you away. I work with a lot of people, and I'm always sad for these people who are scared away by this code, because I understand it. Look at this from a different angle, especially if you're familiar with this code and think, well, what he's talking about. Think about this. Starting from the top, line number 2, line number 5, I have 2 types called isContainer. For starters, this raises the question, what? Why? What's going on here? People are taught that we are using object-oriented programming, so they know what inheritance is. Then they look at this code and they are seeing that my isContainer type in line number 2 derives from something called false type. There is an inheritance going on between these two types. Why? Huh? I mean, yeah, sure, we learned over the time that we use false type here because it gives us all the properties we need later on, call operator and our type internally, which stores the value. Yes, 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 we may know that. But look at what we are writing here, what we are expressing. isContainer is in a relationship with std_false type. All right, maybe I didn't get that. But then look down, line number 17, the second isContainer now derives from stru type. So it's the same thing called isContainer, but it has relationship to different other types. That's a little bit bizarre, don't you think? And then somebody asked this before. We have this beautiful stud void t here. Pardon me, what is stud void t again? And why do I need this to check whether a type is STL container? And inside this void t, oh my gosh, we have in line number 12 to 16 decal type. Well, if you're a library developer, this is what I usually teach my students, then yes, decal type is a thing you use often, but in daily basis of regular code, you shouldn't really use decal type. Maybe we are here a little bit in between, but really decal type here, I mean, why we are now talking about types, decal type. And then, oh yes, we have this decal val t inside. What was that again? So I have to teach that also. Yes, yeah, sure. We know this decal val t thing that creates me an object of t such that I can then call the size method on it and retrieve the type from it. And if that entire expression fails, my decal type fails and spinnays out, and that makes my void t spinning out, and that makes my initial isContainer in line number 2 work. And because it derives from std_false type, we now have access to something that yields to false. I like this language. I really do, okay? I'm not going to bash on it. But from a beginner's perspective, from a teacher's perspective, this is a nightmare. It's great that we could achieve all these things before C++20, but it is a real nightmare. And then look below in line number 21, 22, where I'm testing it with made up struct A and the stud vector of int, : value. Well, yes, thankfully we have C++14 where I can use variable templates to shorten this. But this is another line of code I have to write in between. Nobody knows why it is there, at least not beginners, okay? It's awfully complicated, and to not put it into words, but just in a picture, it makes me really sad, cry, tears. As much as I was happy that I could write this code before C++20. But now let's look about C++20. I'm using a concept here. It's called container. There is a single name container here, not two names as before with the primary template and then the specialization. Only one. And there's no inheritance going on. My std_true type, std_false type, they're gone. That makes it so much easier to see this, what's going on here. And then I'm using a requires expression, we saw this before, to define my requirements. And now in line number 4 to 8, we have the type requirement. This was the one requirement we left out before. And there I now can say, please check that in the namespace of T, there is a type called value type, size type, allocator type, and so forth. And this type requirement is always introduced with type name. It makes me a little sad that I have to repeat this 5 times here, but this is a type requirement, and it's still so much more compact. And the real beauty is in line number 9 to 13. I simply can say t.size, t.begin, because the requires expression on line number 2 allowed me to say which parameters this requires expression takes. And this t comes from my concept t. And I now have access to an object of that t and can call t.size. This code is in so many ways more readable and less scary than it was before. It's really beautiful. And look below, line number 18, line number 19. There is no : value thing, and I don't need to shoot with variable templates on it to shorten it. It just comes out of the box that clean, that nice. So what can I say? That makes me really cheer, really lucky. But I promised you to talk about error messages here. So let's look at another angle concepts try to improve for us. This is the code from the first slide. So this is the C++ 17 version you're seeing here. These are the two static asserts you already know, and this is the third one. This uses a stored array as a container. And as you can see currently, my isContainer check yields false, obviously, because I had to negate the result. So if I remove this not here, the static assert does its job. It tells me that the static assert failed to the requirement isContainer of blah, blah, blah. That's a check for, yes, static assert prevented me to compile this code. But does it help me when trying to figure out why? It only says, well, you're not getting in here today. It doesn't tell me why. Maybe I don't wear pants or something like this. This is the C++ 20 version. If I remove the negation of this check for my stored array, then the static assert does the same thing as before. It prevents me to compile this code, but then there is a note. And this note says that my static assert failed because stored array does not satisfy the concept container. Well, okay. But further, it tells me because there is no allocator type in the stored array. Yes, because that's not a dynamic container. Now I can think about this and can say, yeah, well, maybe my isContainer check is wrong. Maybe it should check for a dynamic container. Maybe I should remove this allocator type check. This narrows it down. This tells me the location of the cause of the error. Where is my concept not fulfilled? And this is something we couldn't achieve with type traits before because they do not really express it in a way that the compiler can understand it. It's just random noise to the compiler that yields the true or false. So this is so much nicer, so much better. We can really cheer about this. Let me check a couple of the questions here. Okay, I think that one was answered. Somebody asking, is there a technical reason for using not with concept and not the exclamation mark? No, it's my personal preference to use the not keyword or the not tokens instead of the exclamation mark. I found this harder to spot over time than the 3-character sequence not. It's a personal preference, has nothing to do with concept. I use this in all my code, typically. And Matthews asks if the output from GCC is equally good to what we see with Clang. Let me recover the already closed tab. So this is GCC here. Oh no, sorry, this is still Clang. And if I flip over to GCC, then they're presenting it in a slightly different way, but in the end, they are saying also that my type name allocator type is not present and this is required. So I personally would say I like the error message of Clang here a little bit more, but I also think it depends. If you're already used to GCC's error messages, then that's probably more their style. And this is a quality of implementation thing, so compilers can do different things here and provide you different quality of their yes or no answer. All right. So there's another thing, new in C++20 or enhanced in C++20, and these are non-type template parameters. We can now use floating point numbers and class types, a limited set of class types, as non-type template parameters. Here's such an example. I have my function fun, which is a function template, and it takes a double as non-type template parameter. This wasn't possible before. And then line number 6 and 7, I now can call this function fun with a positive and negative 0 in form of double. If you look at this, once again, using a good tool, Compiler Explorer, then we can see here, this is the first call, or yeah, this is the first call to fun, this one is the second. We can see differences, and I turned off name mangling here. If I edit demangle, then we can see this is the nice version. And without demangling, we can see what the linker has to deal with, because the linker deals with this demangled version. And this was one reason for the reservation over the years from implementers and from the committee, why especially doubles or floating point numbers were so hard. They increase the length of our names not in the resulting binary, but in what's on our disk when we link these pieces together. And the other question was, shall we support positive and negative floating point numbers? So what should be the representation of floating point number? And the decision was to preserve the correct value. So there is a positive and negative 0. This is why line number 4 and 5 on the right are different. And this is the same for infinity or division by 0 errors, something like this. So the values are totally preserved. This makes it a little bit harder because you're now getting 2 template instantiations for plus and minus 0 in this case. And there are application areas where you like exactly this, and there are others where you may be surprised that this happens. But you're getting the full experience and the full power of floating point numbers here for the non-type template parameters. Now let's look about passing class types. I have a class fixed string here, which is a template taking 2 parameters, a char t and a size tn. Internally, it creates an array of char t of size n, and then I have a const_expr constructor which takes a reference to such a char t array of size n, and it copies this contents into its internal data member. And then in line number 8, I can instantiate such a fixed string struct called fs with the sequence hello, C++20. And I probably would not have presented this code to you in that form in the real conference, because my fear would be too much that you are starting throwing things at me, because there is nothing going on with non-type template parameters here, right? It is. There is another thing going on. In line number 8, we are looking at an increased version of class template argument deduction, CTAD, because before C++20, we would have either to write our own deduction guide here or to specify the types for our fixed string class here, our fixed string object in line number 8. So this is a reduction of code we have to write. But let's move on to the non-type template parameter part. We just created such a class that is allowed to be used as a template parameter. And now I can use this in line number 1 in my template head as a type I specify fixed string here. I give it a name string. And this entire struct template here is named fixed string container. It has one method print, which counts the data of str.data, so that the contents of my fixed string container, of my fixed string class I created before. And then line number 10, I now can create such a fixed string container. And in the angle brackets, I can say hello, world. There is no need to create a static variable first where we store the string in. We can directly now pass it to our non-type template parameter. And for all these, those of you who need a proof, feel free to execute line number 11 fc.print, and you will see that in fact you get the string hello, C++ printed out. So this is an interesting improvement of C++ 20 to non-type template parameters. There's another thing. There's a talk later from, I think it was Roger Orr, about templates. So I think there's not a single conference about C++ these days which hasn't at least one talk about lambdas in it. So I squeeze in a little bit of lambdas in mine too, because they also got improved. This is C++ 14 code here. We are looking at generic lambdas. And the motivation here is I have a max function, or in this case, a lambda, which is assigned to a variable called max, which takes two parameters, x and epsilon, and it tries to figure out which of the two values is greater and returns that one. There is an algorithm in the standard library, so please don't copy and paste this, use the standard library version. This is just helping to illustrate my point. I now can call this lambda in line number 7 and 8 with 2,3 and 2,3.0, and it works splendidly. I personally don't like line number 8 to compile, because once again, we are mixing types here. This is something I normally don't like. Preventing this by using a lambda is tough to impossible in C++ 17 and before. There are ugly solutions using decal type, and they're leading to the wrong result in some cases. So I'm not going to show you this. Let's simply say it's really hard. But let's peek one time behind the scenes using C++ Insights. This is the example from the slide. And if I do transform this, then we can see what's behind a lambda. It's a class the compiler creates for us, and it comes with a call operator. And because we are looking at a generic lambda here, this call operator is the method template. And the compiler creates two type parameters for us, which are then used as parameter types to this call operator. And this is the reason why it's not so easy to constrain this in C++ 17 or 14, because for each auto parameter, the compiler creates a new type for us in the template head. This is the same it does for the abbreviated function template, which we saw before. So this makes it for us impossible to constrain this thing here and saying that x and epsilon should be of some type, but they should be of the same type. We don't care which type it is, but it should be the same. And C++ 20 now comes with templated lambdas, or lambdas with the template head. There we can write after the capture clause in the angle brackets the normal syntax we know from templates. We can give a type parameter here or non-type template parameter, whatever we like. In my case, I'm saying here now type name t, and I'm using t as the type for x and epsilon. And inside the lambda, everything is the same, just that my line number 9 doesn't compile anymore now, because we are looking basically at what we can achieve with a template, or what we could achieve before with a template. And in C++ Insights, if you look at this change is really small. I cannot speak how difficult it was to implement in the compilers, but instead of having the compiler to make up the type and come up with the type name, we just specified it, and it's t. So we then use this name t to specify that x and epsilon are of the same type, and we are done. This is really neat. This is really helpful for all of those of you who use templates a lot, especially the generic templates. Now there are more tricks. There's a really nice one with some fold expressions I like, but we are running out of time here. So let me add this single thing. You don't necessarily have to use only type parameters. You can also use non-type template parameters like in the example below. You can say that you have a lambda, which takes a size t as template parameter, and as its parameter, it takes a std array of type int of this size n, which the compiler deduced before, and I can call now my lambda with a std array of the size 2 without having to say that it's the size 2. This is, once again, bringing lambdas and function templates closer together, and with that, making the language a little bit easier in sense of teaching. It gets more complex in what you can do, but the differences get smaller, so this is really good. Well, at this point, I can say if you're interested more in concepts, I created a cheat sheet consisting of 2 pages, which summarizes and presents all the things I've shown to you and a little bit more about concepts. Head over to my newsletter, subscribe there, and you get it for free. I will be around for questions. I probably will need some time to set up my Discord here because I never used this before. We have a little bit of time left, so if you like, you can probably also ask questions here right now. I will try to head over to Discord and maybe to a remote table where you can approach me if you have more questions, or you can reach out to me on Twitter or write me an email, whatever you prefer. All that's left so far for this talk to say is, I am Fertig. Thank you.